With that said, I would like to just open up and share that I'll be presenting on design of experiments. And this in and of itself, I mean, to be honest with you, this could be a semester-long course or even longer, right? You know, for those of us that have experience in DOE, you know that you're always learning and there's always more to design of experiments. You know, for those that are new to you, know that we're just scratching the surface, and it's going to be a little bit of an introduction, and there's lots to learn, but it's a very exciting field, very powerful tool. And so what we're going to be doing is just kind of touching a little bit on the fundamentals of design of experiments. And I'm going to provide a walkthrough of some of the more common that we'll see in different industries and within the quality field, full and fractional factorials using Minitab. This little snippet, this hour-long talk that we're going to have, or slightly less because I'm going to have time for questions at the end. It's going to be a static walkthrough of Minitab, and what I mean is that I'm not going to be actively pulling up Minitab and walking through. I do have some screenshots here for you, and after the call, I will be providing Mark with a copy of the slides that you can go through, and you'll see as we go through there will be 2 worked examples to where you'll be able to walk through. You can use it and kind of walk through and practice this yourself with Minitab. And as always, for those who know me, very informal, right? Feel free to interrupt if you have any questions. If you want to wait till the end, we'll have time for questions and such at the end as well. With that said, as seen in, right? I don't want to say as seen on TV, right? But recently the RAPS group, the Regulatory Affairs Professional Society, has published the Medical Device Validation Handbook, and I was invited as an author for this topic for design of experiments. So if you are interested, you can find yourself a copy at the link attached. I guarantee you, I make nothing on it. I even had to, in this case, I got a complimentary copy. The previous version, I had to buy my own copy. But you know, if this is a reference that you're looking into, Chapter 5, Design of Experiments is in there. And there's a lot of other great industry, for those that are in medical device at least. There's a lot of good industry applications that are pertaining to validation, but also know that a lot of this stuff, those that are familiar with validation, it's not specific to medical device. Some of the principles you'll be able to apply to other industries as well. So back to our regularly scheduled program, what we're going to go through the goals and objectives of this session, DOE concepts, design of experiments concepts, full factorial designs, fractional factorial designs. In both of those, we're going to talk about the basic concepts, the difference between the two, and then we're going to go through a worked example in Minitab to compare and contrast, and then just show you about exploring more. I should say that this little snippet, this one hour clip, is a pared down version of a course that I offer as well, where we're training on statistical methods in Minitab. But so you'll see that it does very much follow a classroom type exercise. Usually we're doing it live, but like I said, you'll have these afterwards and you'll be able to work through the examples. But what I hope to impart over the course of this 1 hour session is to help you gain an understanding of design of experiments from beginner to expert, right? Hopefully, from an expert perspective, maybe I'll say something a little bit differently that gives you a little deeper understanding. And then maybe for those that are beginning, it'll give you an opportunity to maybe whet your appetite, get a little basic introduction, and want you to explore more. And then we're going to walk through how to perform design experiments with Minitab. So when I talk about experimentation, I want to be very clear that there's a big difference between a study and an experiment, right? Usually a study is, or an observational study, when we're doing scientific method or engineering development, things of that nature. An observational study is collecting data. So we're still collecting data, we're still analyzing data, but it is data from a process or an output that already exists. We're only observing. We're not trying to influence the outcome. Therefore, whatever we see, we may be able to draw some conclusions, maybe some correlations, but we want to be sure, as we always say, correlation doesn't always mean causation, right? So if we're observing something, we see a potential relationship, we could see that there's a potential relationship, but we can't necessarily claim that cause and effect relationship as we can with experiments. With experiments, we're purposefully changing the input to try to influence an output. And if we're able to continually do that, now we can demonstrate with a certain level of, with a high level of certainty that we understand the causation, that cause and effect relationship. So this is where design of experiments is really going to kick in, because at least when I first graduated and I entered the field of engineering, some of the more seasoned engineers, they taught me a different approach to experimentation. The first one was this best guess approach. And that's where, we were looking to study something, we were looking to understand the characteristics of a new component that we were buying. And it was the best guess approach, right? It was basically based on expertise, engineering knowledge and experience with other components. We selected arbitrary factor combinations, we tested, and then made some tweaking adjustments to see what would come out. Very similar, or the next follow-up is what was called the one factor at a time, or OFAT type testing. And this is where we select some baseline. It could start with the best guess approach. And then what we do is hold everything constant, but just change one thing, right? You could change that thing up or down as many times as you like, right? And then once you're done testing that one thing, you reset it back, and then you pick another thing to test, another one of those switches, right? And we can adjust it, to study each factor individually. While these approaches do work, right? I'm not going to say that they don't work. They could be very inefficient, right? Meaning that, especially from an arbitrary approach or just doing one thing at a time, it could be very inefficient and sometimes ineffective. Meaning that, as I said, they might work, but ineffective in that you may miss certain combinations, right? As you're kind of just doing one thing at a time, there could be a combination effect that you're missing, what we call an interaction effect. And properly designed experiments will be fashioned in a way to where we'll not only see the contributions of individual factors, but we'll also see the opportunity of a combination of factors and how they could influence a particular outcome that we're interested in. Design of experiments, in fact, is it's a statistical technique. It's a statistical method. As I alluded to before, you can study this for a semester long. I say that because I did study this for a semester long as I was going for my master's in applied statistics. And there was a course on design of experiments, and we walked through a lot of these different concepts and such. And I could tell you this much: when I got through the end of that semester, I still considered myself a beginner, because the more you learn in this field, the more you find out that there's even more to learn. There's a lot when it comes to experimentation and things of that nature. So as we go through this and it piques your interest, right, keep in mind that there is opportunity for lifelong learning, just in design of experiments alone. So how do we do design of experiments? So let me just go back one slide, and before we go into this last bit, when I talk about statistical methods, right, like any other statistical method, there's some data out there, right? You may need to plan how to get that data. It could be data that already exists and things of that nature. We want to be able to collect that data, organize it in a certain way, analyze it, and then make some interpretation, which is either an inference or a decision. Right? More times than not, when we're doing design of experiments, what we're going to see is there's a couple of fundamental questions we can ask. Is this factor significant? Is this factor or process input something that I really need to be paying attention to? If it is, I characterize it. What is that cause and effect relationship? If I turn the knob halfway, what impact does that have on my output? And last but not least, optimization. What are the best settings for these significant factors or significant inputs? And that's usually what we're looking to draw out of this. And the reason why that's important, and I look at this model, is that properly designed experiments have to be planned properly, right? You don't just collect data and then do the experiment, do the analysis, right? A lot of the value that comes out of your experiment will be determined upfront in the planning. So if you look at this model, when we're talking about collecting the data, you want to design your experiment with how you're going to obtain the data, how you're going to analyze the data. And in subsequent slides, we're going to explore how exactly we do that. And that's where this slide comes in. Right? This slide is probably the first point that you'll want to consider when designing an experiment, right? And this is a simplified version. More advanced courses and things like that will introduce noise factors and things of that nature. But at a very fundamental level, all processes, these black box processes, have one goal in mind. It's to take some inputs that you have, and whether those are material inputs or process setting inputs, things of that nature, there's some inputs that are coming into this process, and they're going to transform those into particular outputs. So in a bonding process, for example, you're going to have the adhesive, you're going to have the materials that you're looking to bond. You may have equipment, you may have heat or other light, other inputs that will help with your curing and your bonding, establish that bond, right? Those are all potential X factors or inputs. Your response, your output, your primary might be a bond strength. You want to establish good bonding strength. It could be a bonding width if you're looking to seal a gap or things of that nature. So these are different potential outcomes that you'll want to consider. And it starts, designing your experiment starts with this model. It starts with understanding what process do I want to study and experiment with on. What are the outputs that I'm trying to achieve? What are the possible inputs that could influence that outcome? And ultimately, systematically, we're going to see that we're going to do a series of experiments. The DOE is not a one and done. We're going to do a series of experiments to help us establish that characteristic equation, y is a function of x, right? Or my outputs are a direct function of certain inputs. The experimental process then, taking that diagram a step further, one is to state, it could be a problem, it could be an opportunity or a goal, right? Problem, we can use DOE and Kappa, or as we're doing investigations. Something isn't quite happening right, and I need to reverse engineer my process. I'm going to define a problem statement that I'm looking to understand. If it's an opportunity from a continuous improvement perspective, I'm operating at this level, but I'd like to achieve a higher level of performance. There's an opportunity ahead. And then a goal could be process development. It doesn't necessarily have to be design experiments for existing processes. You could be in process development and you have a certain target performance that you're looking to achieve. Make that statement. And that problem, opportunity, or goal is going to be around that Y factor. It's going to be about your output process performance. And from there, you're going to select those response variables that you're looking to either resolve or improve or hit a particular target. And then identify those factor variables. As I mentioned before, early on, they could just be possible factors. You know that they're inputs to your process, you know that they're there, but do they have a significant impact on the outcome? We may not know yet. So we may want to consider including those in the study, as well as the levels or the ranges of adjustability that we want to consider. From there, we design and perform the experiment. There are a lot of different designs out there. As I mentioned before, we're going to talk about full factorial design and fractional factorial as one approach, a very common approach. But you're going to design this statistical study that we're going to put together, or the experiment. And then you're going to collect the data, and then do the analysis. And more importantly than the analysis, right, it's not just clicking the buttons in Minitab. It's when Minitab provides an output, how do you interpret it? And we're going to talk about that through some of the examples that we have here. As I suggested before, this is a visual that talks about goals and objectives of a design experiment, right? You know, and not just the goals of what target do I want to hit or achieve, but the objective of the particular experiment in and of itself. In the beginning, I may have a lot of factors, and I don't necessarily know which ones are the most significant or which ones I should continue to go through. So from there, I might use what I call a screening DOE, a screening design experiment. This helps me weed through, like say, yeah, identify the vital few among the trivial many, right? We have a lot of factors and inputs, but you'll often find that maybe not all of them are critical. Maybe some of them we could have at fixed settings, but then there's only a few that we need to adjust to achieve a particular goal. Once we've reduced our model to only the statistically significant parameters or input factors, we could then move on to characterization. This is where we're going to get that magical equation. Y is a function of X, right? Or my output is a mathematical function, a predictable function of my input settings. There's a lot of power and value in this for my validation engineers, right? This is where through characterization, I could establish my process ranges for my OQ testing. For my design engineers, this is where we can determine my limits for my specification setting, right? So there's a lot of value in doing this characterization step to understand that input to output relationship, because then once you understand that, you can do further studies, right? There are further studies that we could do to make it more robust, to make it more repeatable, to optimize our outcome. And that would be the goal of an optimization type DOE. With that said, the fraction, more times than not, your fractional factorial is mostly used for your screening. We're going to see that my fractional factorial allows me to achieve some insight into my process with a reduced number of samples compared to the full factorial. Full factorial can bring you all the way through to the end of this funnel. And then there are other designs that are available that we're not going to cover tonight in the 1 hour, but just know that there's the box bank there's composite designs, response, what we would consider part of the response surface methods that we can use for further elaboration and further refinement of mathematical models. All right, so factorial design. What is a factorial design? Many times, our experiments will require the study of 2 or more factors or 2 or more process inputs, right? It's not just looking at the cause and effect relationship of one variable, right? We don't necessarily need much advanced statistical or design experiments, for a one-to-one type, variable relationship. We could do regression type studies for that, right? But the minute I introduce a second variable or more on the input, and I want to make sure I capture those potential interactions, we're going to want to consider some form of design experiment. And factorial designs are a great way of doing that. They can give you what we call the main effect, as well as the interaction effect relationships. The main effect being that that one-to-one relationship, right? This particular input factor has this percentage of an effect on my outcome, but the interaction effects is this combination of these 2 factors, right? One set a little higher, one set a little lower, may have a unique or an impactful outcome and on my output. And the factorial designs will give you both of those insights. When I talk about an effect, what we're talking about is an average change in response with the change of those factor levels. Meaning that if I move something a little bit up or down, what influence does that have on the outcome? And we're going to see mathematically how that's going to result through the Minitab examples. I I mentioned, we talked about full factorial designs as well as fractional factorial designs. Full, by definition, includes all possible combinations of each factor, right? So if we have 3 factors at 2 levels, that'll give us 8 different combinations. And if we have the time and the resources to do so, we may choose to go that route. Fractional factorial designs will just include a portion of those, maybe half or a quarter of the or less, right, depending upon how many factors that we have of all possible outcomes. Now, just because we have less, doesn't necessarily mean we're not going to be able to find the answer. We're going to see that later on. But it does handicap us a little bit, right? We, with less samples or with less combinations, we do lose some insight. But nonetheless, there is still some value to be gained. And we're going to talk about those differences. The other key factor that we're going to want to know that's going to differentiate the two between the full and the fractional factorial is what we're going to call resolution. Full factorial, we don't have to worry about resolution. We have all the possible combinations, so we know how the process is going to respond with those different combinations. When we move to the fractional factorial, as I mentioned, we may remove half of those combinations, or even 3/4 of those combinations, or more, right? So we're only working with a small portion. With that, when I say we lose some insights, what we do is we lose some discernibility. Resolution is going to be a level of confounding or aliasing, meaning that I may see a response, but it could be attributed to one thing or another. And we're gonna talk a little bit more about that, but that's what resolution is going to be, right? Meaning that full factorial, it's clear, I have all the combinations and I know what response came from which combination. But with the fractional factorial, since some combinations are missing, I may not be 100% certain if the effect that I'm seeing is due to the combination that's there or the combination that's missing. But there are ways to kind of work through that as well. We'll see. All right, experimental notation. This is just kind of how you're explaining your experiment and things of that nature. Doesn't really, you really don't need to know too much about this when it comes to the practical application of Minitab, but as you're writing up your report and things of that nature, and we're talking about experiments, I like to use this little mnemonic: levels lie, factors fly. And it does give you some insight as far as how many experiments you might be talking about. So for example, and more times than not, we're going to be starting off at least with 2-level experiments, right? Meaning a high and low value that we want to adjust our factors. And is this first example, let's say I have 5 different factors that I want to explore. By following that little mnemonic, levels lie, factors fly, I set up an exponential term. 2 to the 5th yields 32. 2 to the 5th equals 32. That tells me that if I want to do a full factorial, I would need to do 32 unique experiments to collect all the data I need to do this analysis. Now, 32 might start becoming a little time consuming, a little cost prohibitive or schedule prohibitive, in which case, especially if this is a screening exercise, I may want to achieve the same insights with less rigor, with less burden. I can do that by saying I'm going to take 2 to the 5 minus 2. Right? 5 minus 2 yields 3. So 2 to the 3 would be 8. And what that tells me is with 5 factors and 2 levels, I can get some good valuable insight with only 8 runs, but this would be considered a quarter fraction factorial, where we're only running a quarter of the possible combinations that we would have if we did the full factorial. Again, we're going to see that there's still value in this. We're still going to be able to garner good information from these fractional factorials. Just diving a little bit deeper now into some of these terms and some of these tools or outputs that you would see from Minitab, and more importantly, the interpretation, right? The interpretation that we're going to see here. I mentioned before main effect plots, and this is where we want to see the average effect or the effect of individual factors in our study and what impact that they have on our response or the output of our process. These main effect plots will not only give us the relative strength of the difference, but also the direction, right? Is it a positive correlation or a negative correlation? In this example here, what we could see, if I look at my y-axis being the response, the process outcome, and then along the x-axis, it's my low and high settings, right? Whatever they may be. It could be a lower temperature, high temperature, low pressure, high pressure, whatever your process setting is. It could be attribute. It could be product A versus product B, in which case it doesn't necessarily matter high, low. It's just whichever one you assign. And what we could see is the relationship. The steeper the curve, the steeper the line, the stronger the effect that we have here. What we see here on this, factor A, the first factor here, it's probably got the steepest line, and it has an effect of 4, meaning that starting from my overall swing, the overall swing, the overall effect of going from my low to high is an increment of 4 units in the positive direction, right? Meaning that as I go from the low to the high, I'm going to increase by 4 units of my response. For the factor B, we see that going from the low to high, I'm actually going to decrease by 2 units, and then EC being an increase of 1 unit. So here too, we'd have to do the statistical analysis, determine if there's statistical significance of these, but we could see the relative strength, right? Factor A has a much bigger effect on my outcome than the other 2 factors potentially combined. But I say potentially because what we want to look at next are potential the interaction effects. The interaction effects is what happens if I change 2 factors at a time, right? What influence can the different settings combinations be? And once again, relative strength and direction. Intuitively, pulling the effect from these is not quite as easy as it is in, say, the main effect. But what I will share with you, kind of in this, first time around is what to look for in the interaction plots is whether you have parallel lines or crossing lines. With your parallel lines that you have indicates that there's no interaction between the 2 variables, right? So it really doesn't matter, that interaction. Whereas if they're crossing or if it appears that they're going to cross maybe beyond this range, then you would assume that, or you can conclude that there is an interaction between those 2 variables. So, for example, in this one, the interpretation would be there's definitely an interaction between factor A and factor B. It turns out to be a strong interaction. Factor B and C, you don't see that strong crossing. You do see that they converge. There still is an interaction effect, albeit not as strong as the interaction between A and B. And then factors A and C, there's 0. Those are parallel lines, and there's 0 interaction. From these, we can put together that characteristic model. And I know I'm kind of emphasizing Minitab. There are other software packages and things of that nature, that can do this. But the math behind it is essentially calculating these effects and then using what we call the half effects. We multiply each effect figure by 0.5, by half. And then what we do is we set up this characteristic model. So we can see here, and it'll be very apparent from the main effects plot. In my main effects plot, I could see that the average line, the middle line, is 10, meaning that I'm starting off at a baseline of 10. And whether I go up or down, I'm going to either increase or decrease by that factor. And that's where the half effect comes in. So I start building out my characteristic equation with that baseline of 10. And then I start adding the half effects, plus 2A minus B plus 1/2 C, and so on and so forth. And I start building that out. That's what the software is doing for us. Yes, we could do this manually, but why do that when we have software available? That kind of makes it easy for us. So that's an insight as far as what's happening with these factorial designs. And what I'm going to do now is, you're going to see we got a ton of slides. I'm going to rifle through them very quickly. I'm just going to have a couple talking points, kind of just emphasizing. But again, the slides will be made available. I believe we usually, if there's a recording, that's often made available as well. And then, of course, as you're going through it, if you have any questions, you can always reach out to me, and I'd be more than happy to guide you through. But the best way of learning is by doing. And again, this example is going to be in Minitab. If you have other statistical software, it will be similar steps of how to set it up. It just might be different clicks and keystrokes and such to kind of get there. So let's start off by a full factorial design. I'm going to start off slow just to set it up. Once we start seeing the screenshots, I might go a little bit quicker just to kind of get to the punchline and the conclusions. But this is an example of what a full factorial design could look like. This is where we have 3 factors. And again, these could be, most companies are packaging some kind of device or component, right? So in a packaging environment, I might have time, temperature, and pressure, right? So these factors represent particular process inputs. And then my response could be a particular process output, again, following the same example of a packaging seal strength, potentially, right? Those could be examples, or yield, whatever figure that you want to use and maximize it, and or optimize. I'm saying maximize because I'm looking for this particular example. What we're going to do is we have our full factorial design. We talked before that 3-factor full factorial would result in 8 little mini experiments that we're going to combine into one. And then we want to define our goal. In this particular case, we want to maximize the response. We're saying that more is better, and my goal is to maximize the response. So this is the experiment. I'm visually showing tabular, what that would look like, and I talk about different combinations. So, for example, the first run would be all low settings. The negative indicates, my low setting for each factor, and then a response would be the data that would result if I had those settings. When I run those settings. So how do we do that in software? So as I mentioned before, you see this activity 3.2. It is this is one of the classroom exercises we do as part of our training on this. But you don't need any files. You're going to see that everything in here is self-contained. You're going to be able to run the simulation following these steps. So the first thing we would do is we want to create the full factorial data sheet, and then we're going to collect the data, right? I'm going to provide you with data that you would enter as if you were running an experiment. Analyze the full factorial design, so we'll kind of walk through the keystrokes on how to perform the analysis, how to interpret the results, and then we're also going to talk about, we're going to introduce reducing the model and a nice little tool that we have also built in the Minitab, response optimizer. So in Minitab, there's a DOE function, right? And basically clicking through the DOE to factorial, and then we would create a factorial design. And then from here, we have to select the design that we're going to have. And we could see here, before I say that, before we select the designs, we do have to select the number of factors. In this example, it was 3 factors. And then we would go on and click the design button to open up my choices. And we could see here that if I had 3 factors, I have 2 options available to me. I could either run a half fraction of only 4 runs, or I could run the full factorial with 8 runs. We're gonna run the full factorial. So we select the full factorial, we click OK, and then from there we start configuring our experiment, our data collection sheet. In this example, it's going to be very basic, right? But what I'm going to talk through is once we click that factors button, is we're just going to name A, B, and C, factor A, factor B, factor C. But if you were really doing this, and again, following that example of a packaging seal, we may put in time, temperature, pressure, right? So we have some physical engineering inputs that we can consider and relate to when we're running and setting up and running our experiment. For here, just for demonstration purposes, factor A, B, and C, we click OK. And then we go into our options. And in our options, we're going to deselect randomized runs. Now, disclaimer here, in practice, you probably don't want to do this, right? Unless for some reason randomizing the runs is completely detrimental to production when you're trying to run these and things of that nature, right? But if there's no practical reason why you couldn't do randomization, you want to do that. It just helps prevent bias in your study. But for this demonstration, and as you go through and you try going through these steps by yourself, I'm going to ask to deselect the randomizing the runs, because that way I could predict what your outputs are going to be or what your design is going to be, and then when you input your data, you're going to have the right matching. So that's the only reason why, for demonstration purposes, we're deselecting the randomization of runs. And then from there, we click OK and we generate the design. And what will happen is in Minitab, it'll create, there'll be a little output up top that talks about the design summary, but more important is the data collection sheet that you're going to have below, right? Minitab will automatically create this data collection sheet for you and recognize it as a factorial design experiment. Once you have that set up, we're going to run our experiment, collect our data, and this is the data that we want to put in. So when we have this set up, we would rename column 8 response. We put a little title there. Again, if following that example of the packaging, this could be seal strength. And then we put in the numbers. Once the numbers are in there, and again, from a practical standpoint, I'd go off and I'd physically run my experiment. I'd collect my data, and then I would just put it in this sheet. From there, we run the experiment, or we analyze the experiment following a similar path, DOE factorial. Now I'm going to analyze the factorial design, right? As I mentioned before, it recognizes that's a design. So now we're gonna invoke the analysis. And what we want to do is we want to make sure that all the terms are included in the model, at least at first. So before we go ahead and click OK to run the analysis, we want to put the response in the response field, and then we want to click this terms button. And then that terms button will open up this dialog box for us. And if we click on the double arrow to the left, from right to left button, what that does is it pushes everything that we have in the available terms. It pushes it into the selected terms. And when we have this selected to the maximum number available, it will give us every single combination. So it'll give us factor A, B, and C, but it also gives us the AB interaction or combination, the AC combination, the BC combination, and even the ABC combination. Once we have that in there, we click OK. And what that does for us is that makes sure that Minitab includes all factors at least first time around, we're going to see in the analysis. Then from there, we click OK, and the analysis comes out. Now, a couple things to note on this on this output. One, first and foremost, at the top is a regression equation. I mentioned before, right? I showed you how to build out that characteristic equation where we have some constant plus some coefficients times each factor as well as each combination of factors. And Minitab calculated this very right, and just in seconds, right? We'll calculate this this equation for us, and it's a very long, complicated equation, right? And if that's what it is, that's fine. But what we see more importantly, which is interesting, is in our Pareto diagram here, in our Pareto diagram, if this red line represents the level of statistical significance, we see that only 3 of these bars cross that line, and some of them are insignificant. Now, I could go back and manually remove some of these factors, but what I want to show you is that Minitab will also do that for you, right? It'll automatically remove insignificant factors for you as part of the analysis. It has an engine where it runs multiple iterations of the analysis, removing the insignificant factors. And the way we invoke that is still the same way, right? So we still go through our DOE factorial, analyze factorial design. This time we go into our terms, right? And then from here, what we do is, oh, I'm sorry, this is the manual. This is the manual way of removing it. We're gonna manually remove the two-way, three-way, and then we use that one button that basically pushes everything from the selected terms and pushes those back over. So we're pushing the AB, AC, BC, and ABC back manually. We click OK, and then here we get our outcome. And what we could see here is that the regression equation is much simpler now, right? Which again, it's both equations were valid. Both equations were valid. But when you have an opportunity for something easier, we'll go with something easier. It's also much easier to interpret, right? Here, we're only influencing factors A, B, and C. So we're directly controlling those three knobs on our piece of equipment or what have you. And it's easy to understand. And we also see from the Pareto diagram now that all terms are considered significant. The factorial plots, we can view those as well. And as we could see before, right, I mentioned that we could see relative strength. And we can see here factor A and factor B have relatively strong positive influences on our outcome, meaning that as I increase our values in A and B, we'll also get an increase in the response. Whereas C has a negative correlation. And negative doesn't mean less. As we can see here, it's actually the strongest out of the three. It's got the steepest slope. But it is negatively correlated, meaning that as I increase C, I reduce my output. And then here we could see that the lines, for the most part in the interaction plot, are mostly parallel, further supporting the fact that we don't have any significant interactions. So this is more interpretation part, right, when you see your output. And last but not least is that response optimizer. Response optimizer will automatically tell you, if you couldn't tell already from looking at it, right, what are the optimal settings. In order to get there, what we go again is in our DOE factorial menu, and then we scroll towards the bottom and we see response optimizer. We click that to get a dialog box. And as I mentioned before, we need to determine our goal, and our goal in this case was to maximize. You also have the option to minimize or to set some target, some range, or some specific value that you want to achieve. So we go ahead and click OK once we select the maximize. And what we see here is the outcome. And it will automatically give you the optimization. You could play what if scenarios where if you wanted to make adjustments in these red settings, you can make adjustments to see what you could get. And the response optimizer will estimate the outcome, this Y value. And it does so using that same characteristic equation that we had before. Response equals some constant plus a combination of my factors. And what we could see here is that the optimal settings is a high value for A, a high value for B, and a low value for C, for factor C. Now, if we did that, the model indicates we would expect to see a potential outcome of 99.5. When I look at that on my original data collection sheet, high output, low output corresponds to 100. That's pretty close, right? We were predicting 99.5, and in practice, we achieved 100, which is, for all intents and purposes, very close. And, just further supports that the model that we generated would be able to predict, a particular outcome. Now, why is that important? And we'll go through this a little bit quicker so that I make sure we have time for questions at the end. One, first and foremost, I mentioned before, there's a benefit of doing fractional factorials in that we don't have to do as much, but it comes at a cost, right? A little bit of confounding through the resolution of the design. What is resolution? And I'm going to try to explain that pretty quickly to just get an understanding of what type of information I lose and how we could deal with it. So this is where, so different levels of resolution. Resolution 2, theoretically it exists, but in practice we would never come across it. We would never do it. We would never design an experiment because resolution 2, I'm going to use my hands here, right? it basically takes one main effect and confounds it with another main effect. That's where the 2 comes in, right? I got 1 and 1, 1 plus 1 is 2. I can't tell the difference between factor A and factor B, or factor B and factor C. It's a useless design, right? There's no good value in it. Like I said, theoretically it exists, but in practice we would never do this. What does exist, and again, you might ask yourself, well, this resolution 3, right? This seems maybe a little weak, or you know, why might I do this, right? This is where I have a particular one main effect with a two-way interaction, right? Again, using my hands, right? 1 plus 2 is 3. The different main effects could be confounded or confused with the two-way effects. Meaning, I'm not 100% sure if the output that I'm seeing was because what I did with factor A, or because of what I did with a combination of B and C. We typically use these for screening designs because I'm looking to potentially omit some main effects that don't matter. So we'll typically reserve these for our screening type designs. But then we'll want to build up a higher resolution design to get more information as I'm doing characterization and optimization. Resolution 4 now, right? If we follow that pattern, resolution 4 is a little bit stronger in that my one-way effect is now confounded with, say, a three-way effect. Three-way effects are less common than, say, two-way effects. So from there, if I see A or B, C, D, I'm leaning a little bit more towards A, right? It's probably more likely A. Similarly, if I have B with A, C, D, again, I'm going to lean a little bit more towards B. Now, we can also have two-way effects confounded with other two-way effects. But here too, if I'm pretty confident in my main effects, I probably have all the information I need to pull out of a resolution 4 design. Last but not least, 5 and above, right? 5 and above, those are very, very insightful experiments, and this is where that main effect, right, a factor of 1, is confounded with a 4-way effect, which is very rare. I'm not going to say it's impossible, but highly unlikely. So if you see the effect there, there's a very good probability that it's with the main effect. And similarly, 2-way effects are more common than 3-way effects. So if you see that type of confounding, you could probably assume it's more of a 2-way effect. How do you decide, right? Again, Minitab will walk you through it. There's a different list of factorial designs in here, a table here that shows you how many factors you have, how many runs, and what resolution you may be. And I mentioned before that 3 is kind of coded red. It's pretty good, right? It's good for some purposes, not for all. That level 4 is yellow, right? It's pretty good. But 5 and above, excellent, right? Green, you can really garner a lot of good information. All right, I'm really going to rifle through this because we only have maybe about 10 minutes or so remaining. But what I want to set up is it's essentially the same data set, only half, right? So what I have here is the same factors. I have the same responses, but I'm only going to give us half of those. This is going to be considered a resolution 3 design, but let's see what kind of value we get out of it. Same setup, right? So this is where we'll be able to go real fast because it's essentially the same steps. We're going to set up a data sheet. We're going to put the data in, we're going to run the analysis, reduce the model, and then we're going to draw some conclusions. So this is us setting up the data sheet. We're going to run through the different designs. Here is where we look at those different designs, and this is where we learn that it's going to be a Res 3 that we're going to do. We select the resolution 3, we click OK. We rename our factors, factor A, B, and C. In our options, again, we're going to de-randomize the runs so that we can predict what the worksheet is going to look like each and every time we run this little exercise. We're going to click OK to create the worksheet. So now what we see, same idea. There's a little bit of an output here, but more importantly, there's a data collection sheet. Now with only 4 lines instead of 8. The same idea, we're going to put that data into the worksheet, and then we're going to run the analysis. In here with the terms, again, we're going to push everything over to the available terms. We're going to click OK. And in this case, Minitab already recognized and said, hey, you know what? You got some level of confounding. We can't tell the difference. So we're going to give you the characteristic equation in terms of main effects only. So this is already the reduced model. that we would have. And again, we can once we have the model in Minitab, we can invoke the response optimizer. Again, we're looking to maximize the response. And what we see is, interestingly enough, Minitab gives us the same outcome. It tells us again, hey, for this particular data set, for this experiment, a high factor of A, a high level of A, high level of B, and a low level of C is the best settings, right? So it gives us the best settings. It predicts that that outcome would be 99%, 99 instead of 99.5. But what I want to show is, more importantly, is that combination was not even included in this study, right? This is an example of, going back to earlier slides. When I did one factor at a time, the best solution, I may have never even tried my best solution, but using one factor at a time approach, I never even know it because I didn't try it. Using fractional factorial designs, even if there's a combination, a best combination out there, I could still find it even though I don't test it, right? Now, in my validation studies, I'll do a confirmation run at that to make sure that I do perform there. But with less samples, I could still get that insight as far as where my best settings might be with these significant factors. So that's the big punchline, right? That's why, I really love, it's good to kind of walk through the full factorial so that we understand, what information you get. But as you increase, right, as you increase different factors, your number of experiments, your number of runs will grow exponentially. Just know that you have those fractional factorial designs available to you where you can still garner great information. With that said, again, I think I landed to the point where we still have a few minutes to field some questions. Feel free to reach out to me on LinkedIn, follow our business page, connect with me on LinkedIn, and reach out. But now I'll open it up, Mark and team, to any questions that you may have.